We're good to go, Alice? Cool. All right, welcome to another edition of our Theory Lunch. Today we're very happy to have our own Vitercik, who will talk to us about differential privacy and auction design and some other topics related to that.
Okay, so I'm going to talk about differentially private, algorithm, and auction configuration. And this is joint work with Nina Bolkin and Travis Dick. So I'm going to start off with some examples of how privacy might be leaked in algorithm configuration and auction design, which might seem pretty unrelated right now, but I'll show how they're connected shortly. So suppose that you live in a small town, and this small town has a pharmacy. The way that this pharmacy prices its drugs is looks back at the demand for those drugs over the past month, and it prices the drugs as a deterministic function of the demand over the past month. The price of this drug for this embarrassing disease has been $1 for many years, and a family moves to town. And not long thereafter, the price of this drug goes up to $100. So you can be pretty confident that probably someone in this family has this embarrassing disease. And so more generally, as is pretty obvious at this point, big internet companies do use our purchase information to set prices. And prices learned from purchase histories can reveal sensitive information about individual purchases. So we need a way to privately set prices and design auctions based on purchase histories. Now I'm going to give an example of privacy leaks in an algorithm configuration and parameter tuning scenario. Parameter tuning is a huge topic of research in machine learning these days. So suppose you're a lab technician and you're going to work, and on your way you notice that a celebrity has just checked into the hospital. So you go to work, and that's you at work, and you get a memo, and it says, "Dear lab technician, please update your default Cplex parameters to something." And you know that the IT staff at this hospital tunes these parameters so that problems related to the specific individuals in this hospital, those problems will do well when Cplex is run to solve them. And suppose a parameter correlates with a certain disease, then an attacker can infer information about the medical records that were used to tune those parameters, tune those algorithm parameters. So you might be thinking right now, how on earth could I possibly go from this model, these parameters, these prices that are learned from data, and use just this model to go back and learn sensitive information about the training set? How could I do this? Is this possible? Well, as it turns out, many works have shown that it is possible to infer sensitive information about the training set from a machine learning model. It's possible to invert these machine learning models. So for example, Calandrino et al. Showed that by observing a series of recommendations from websites such as Amazon, an adversary can infer individual purchase histories. And it can do this inference with very high accuracy. So just, these recommendations are based on your purchase history. So this paper showed you can go from these recommendations back to the purchase histories with high accuracy.
This is for one person. So you look at the recommendations for one person and that for a purchase history.
Yeah.
One person.
Okay, so this is one example. Here at CMU, Matt Fredrikson showed that it's possible to extract images of training subjects from a facial recognition system. So this is a facial recognition system built on neural networks, and basically it takes images of individuals. These individuals are in some data set, and it learns a function which takes a set of pixels, a new image, and says, well, I'm 90% sure this picture is of Bob, I'm like 5% sure it's of some guy, Tom. It returns a confidence vector of the individuals in the database. And so what Matt Fredrikson showed is that if the attacker has access to a name of a person in this database, so maybe the name is this guy, Bob, this image was used to train the classifier, train this neural network. So it has access to this person's name and access to the facial recognition system that returns some class confidence score. It was able to extract this image of this guy in the database just by using his name and this black box access to the facial recognition system, which I think is pretty amazing. Like, these are pretty similar given kind of the black box access to this facial recognition system. One last example of going from the machine learning model back to the training set. Matt Fredrikson also showed that it's possible to invert a machine learning model to learn sensitive genomic information about the people in the training set. So this is in like the personalized medicine domain. Okay, so in response to all of these attacks, computer scientists have developed private machine learning algorithms. So they protect the information of the people in the training set. And generally speaking, these existing machine learning algorithms apply to optimization problems defined by well-studied, well-understood functions in machine learning. So like maybe these are like convex optimization problems or like L-Lipschitz, something like that. But what do we do if the objective is non-convex, non-differentiable? How can we still do private optimization in this setting? Yeah.
I have a question. The case of Amazon, I'm looking at what their recommendation is.
Yeah.
Is that really deciding if a person belongs to a person? Because it feels like many people have been used to come up with some sort of classifier that will go from history to recommendations.
Right.
So necessarily like seeing somebody's, like this is like X and Y, doesn't necessarily say whether that person XY was included
In the training set. No, I'm just showing like you learn recommendations. I'm just trying to like exemplify like you can learn recommendations based on this person's purchase history. So you can go from the recommendations back to the purchase history. Okay. So what do we do if this learning objective is non-convex and non-differentiable? Well, in our work, we provide a private algorithm that maximizes data-dependent piecewise Lipschitz functions. And I'm going to describe what this means soon. But this private algorithm has applications both in algorithm configurations, so that example I showed in the beginning, where we're tuning parameters based on a set of individual medical records. And also, our algorithm has applications in pricing mechanism design and auction design. And the reason why our algorithm applies to both of these kind of different settings is just because algorithm configuration and mechanism design often reduce to maximizing a piecewise data-dependent Lipschitz function. So that's exactly what our private algorithm is able to maximize. So what I'm going to do next is I'm going to describe give a high-level idea of what we are able to prove for algorithm configuration and auction design. Then I'll talk about what do I mean by privacy. I mean differential privacy. And then I'll give a kind of more specific example of what differentially private pricing design means. So first, learning-based algorithm configuration. The goal here is to tune algorithm parameters to achieve high performance over a specific application domain. So you don't want your application to do well in the worst case necessarily, but you want it to do really well on your specific application domain. And algorithm configuration has been studied for decades, and it's led to breakthroughs in combinatorial auctions, scientific computing, vehicle routing, and SAT. And kind of the high-level model is as follows. So we've got some application-specific distribution over problem instances. So this might be like a collection of maps in a city that a city planner sees like over the course of a year or something like that. So an algorithm designer gets a sample from this distribution of maps, and he wants to use this set of samples to find an algorithm that's best for their application domain. So it's best for like facility location in cities in like Western Pennsylvania or something like that. And when I say best for the application domain, I mean best in expectation over this application-specific distribution. So that's the high-level idea of learning-based algorithm configuration. And we show that our private algorithm has strong utility guarantees for many algorithm configuration problems. So just for example, hard combinatorial problems come up in diverse application domains where privacy preservation is important. So for example, maybe an online marketer uses the knapsack algorithm to figure out what bundles of deals to give individuals. If it tunes its knapsack algorithm so it does really well on the kind of individuals that visits its websites, then maybe that algorithm configuration reveals information about those individuals that visit its website. And these hard combinatorial problems are often solved approximately by greedy algorithms, where elements are added iteratively to a set, a solution set. So for example, in knapsack, this iterative addition procedure is according to some heuristic, and in knapsack, that might be the size of the item divided by the value of the item. So you want to kind of add them iteratively according to like bang for the buck. So I'm sure you guys have seen this before. And Gupta and Roughgarden in 2016 and 2017 proposed an infinite family of greedy heuristics for the knapsack and max weight independent set problem. So this is just the same heuristic, except I've added a row parameter at the bottom there. And in this paper, Gupta and Roughgarden show how to tune this parameter according to like the specific application domain. And our private algorithm uses sample problem instances to find a nearly optimal greedy heuristic for the specific application domain, and no sensitive information is revealed about the training set. Yeah.
So when you say near optimal, is that like a formal guarantee, or is it just like the performance wise when you take is it based on is on us to use the best parameter tuning versus our parameter tuning and compare it to that?
Yeah, I'll give a formal bound on if you use the best parameter tuning and our like private parameter tuning. What is that bound on utility? The utility is kind of an abstract function that you get to decide. So another example of an algorithm configuration problem that we look at is integer quadratic programming algorithm configuration. So IQPs are used in many applications where privacy preservation is essential, like financial or portfolio optimization. And as you probably know, but if you're not familiar, don't worry about it. IQPs are often approximated by an SDP, and we round the vectors to get an integer solution to the original integer quadratic program. And there are many different rounding schemes with varying qualities. So like S-linear rounding functions by Feigen, Langberg, and outward rotation rounding schemes by Zwick. And what we do is our private algorithm uses sample IQP instances to find a nearly optimal rounding scheme for the specific application domain. And no sensitive information about the training set is revealed. So I'm not going to talk about SDPs, so if you're not familiar, it's okay. And so that was algorithm configuration, and now I'm just going to say a few words about mechanism design. Learning-based mechanism design, the goal is to use information about past consumers to design auctions and prices that will achieve high revenue over future consumers who are similar to those past consumers. And of course, learning-based mechanism design is employed throughout industry, and it's garnered significant attention in the theoretical computer science community as well. So now I'm going to talk a little bit about what do I mean by privacy, and I mean differential privacy. So differential privacy is kind of an incredible success story from the TCS community. Like Apple claims that it's now using differential privacy in its iPhone software, and like it employs differential privacy engineers. So yeah, it's an incredible success story. And in words, an algorithm given an input data set D is differentially private if the following holds. The output reveals almost nothing more about a record in the data set D than the output would have if that record was not contained in D. So that's kind of in words what differential privacy illustrate it in a picture. So let's say I have this data set consisting of Alice's records, Bob's records, Claire's records, David's records. This is my data set, and I feed it to an algorithm. And differentially private algorithms are by definition randomized, by necessity randomized. So this algorithm is going to output a solution to whatever problem I'm trying to solve according to some distribution. So this is like the distribution over outputs that this algorithm gives when I feed it that data set. And so what did I say differential privacy is? Algorithm is differentially private if the output reveals almost nothing about a record in D than the output would have if that record wasn't in D. So that means, let's say I remove Claire's record. This algorithm should reveal nothing more or less about Claire than it did before I removed her record. So again, after I've removed her record, I feed the database to the algorithm returns an output according to a distribution. And differential privacy means that these distributions over outputs should be close. So that's kind of in a picture what differential privacy means. And now I'm going to just tell you what it means in math. So this is the definition of differential privacy. An algorithm is epsilon delta differentially private if for every pair of neighboring data sets, D and D prime, so a pair of data sets is neighboring if it differs by only one record, like before I removed Claire's record, after I removed Claire's record. So for all pairs of neighboring data sets, D and D prime, and all sets O of outputs to that algorithm, the probability that the algorithm, given data set D, the probability that it returns an output in O is at most e to the epsilon times the probability that the algorithm, given that data set D prime, neighboring data set, the probability that that output is in O plus delta. So like you can just see the epsilon and the delta are just like kind of multiplicative and additive terms showing how close these two distributions are. And I think e to the epsilon is a little weird the first time we see the definition of differential privacy. We're not used to seeing this as a multiplicative approximation guarantee. So e to the epsilon is like approximately 1 plus epsilon, and which is a more familiar multiplicative approximation guarantee. And e to the epsilon, like the math just works out better if we use e to the epsilon. So that's why you see it in the definition of differential privacy. Okay, so that's differential privacy. Any questions? So now I want to talk a little more in detail about what I mean by private pricing design. Like I said, our algorithm does private algorithm configuration and pricing design, but like I've told you what differential privacy means, but what does it exactly mean in these contexts? I'm going to tell you with a really simple example. So this is a single item pricing problem where there's one good ticket for sale, this coffee. There's a distribution over buyers. So maybe this is like the distribution over buyers that go to like the Starbucks on Craig Street. And that Starbucks is trying to figure out how to price its coffee according to this distribution. And I'm just going to denote the buyer's values as like this is this green person's value for the coffee. Okay, so what revenue can I extract from a person given a certain price row? This orange person is going to buy the coffee. They're going to be willing to buy the coffee if their value for the coffee is at least as much as the price, right? Once the price goes above their value, they don't want to buy the coffee anymore. So the revenue I can extract from this orange person is the price times 1 if they're willing to buy the coffee, 0 if they're not willing to buy the coffee. Okay, so our learning-based algorithm, pricing algorithm, receives a set sampled from that distribution over buyers. And its goal is to maximize average revenue over the sample. So like, this is just like average revenue over that sample over buyers. And the reason the pricing, this learning-based pricing algorithm wants to maximize average revenue is just because learning theory tells us that this value of rho, if we find the value of rho that maximizes average revenue, then this value of rho also approximately maximizes expected revenue. Like in the end, we want to maximize expected revenue.
Yeah, the expectation there is taken over the distribution D,
Over
right?
bias. Yeah, yeah. Yep, same distribution. So, just going to give an example. So we've got a set of 1 buyer sampled from this distribution. Their value for the coffee is 3, so they're going to be willing to buy the coffee until the price of the coffee hits 3. So this is the amount of revenue we can extract from this blue person. Okay? Let's expand this sample to include also an orange person. Their value for the coffee is 4. So I've just drawn the amount of revenue we can extract from this orange person in the orange line. Okay, and remember, our pricing algorithm wants to maximize average revenue over the sample. So I'm just going to take the average of the blue line and the orange line, which is this. And you can see that the price that maximizes average revenue is $3. But like everything about this curve, this average revenue curve, has to do with the sample, right? Like the breaks between the piecewise portions has to do with the sample. The output price has to do with the sample. If I just return 3 as the price, it reveals a lot of information about the sample. So I can't return 3, right? Because just this function has everything to do with the sample. If I change the sample a little bit, this function is going to change a lot. So we want to write an algorithm that gets average revenue as close to 3 as possible while preserving differential privacy. Okay, and I want to talk about this, like I said, we do algorithm configuration, we do option design. I want to talk about this a little more generally for the rest of the talk. So instead of average revenue, I'm going to talk about average utility. So super abstract function, average utility, use of S of P. The S is the data set, the original data set I have here. So it's the utility of that parameter rho, which is on the x-axis over that sample, average utility. And on the x-axis, I have just some parameter rho. Okay, and now I'm just going to describe the general problem one more time to make sure it's clear. So we've got a piecewise utility function that depends on the sample, use of S of rho. So maybe it's average revenue over the sample as a function of the price. And we want to privately find a parameter p hat that approximately maximizes this data-dependent function. So I've got this sample. That sample defines a utility function, use of S. I feed this utility function to an algorithm, and this algorithm returns a distribution over outputs. And if I change this sample a little bit, I've got a new utility function, use of S prime. The new sample is S prime. I've got this new utility function. I send it to the algorithm as well. These samples are very similar, so the output distribution over parameters should be very similar as well. That's our goal. Any questions? Because I'm going to talk about this algorithm I've been mentioning now. So I'm going to talk about the algorithm. This algorithm has 2 parts. I need to ensure it preserves privacy, but I also need to ensure that it gives a good parameter, like a parameter that approximately maximizes average utility. So first, I'm going to talk about the privacy guarantees. One of the nice things about differential privacy is that we don't have to start from scratch every time we want to write a differentially private algorithm. There are all these kind of classic algorithms that we can rely on that preserve differential privacy. And one of those is the exponential mechanism, which was presented by McSherry and Talvar in 2007. And the exponential mechanism says, pick a parameter vector rho. I'm talking about, like before I was talking about one-dimensional parameter spaces, but I'm talking generally about multi-dimensional parameter spaces now. So pick a parameter vector rho with probability proportional to e to the c times epsilon times the utility at rho. Epsilon is our privacy parameter, and c is something that doesn't matter for the rest of this talk. And the guarantee that McSherry and Talvar give is that if you do this, then you're going to be preserving epsilon differential privacy. Epsilon 0 differential privacy. These are our privacy parameters. So it's pretty good. Okay. And sampling from this exponential mechanism is really easy when we can calculate its antiderivative and the parameter space is one-dimensional. So I'm not really going to talk more about this, but it's easy to do when it's one-dimensional. But when the parameter space is multidimensional, sampling is hard. So what do we do? Well, there are existing sampling techniques that are efficient for log concave distributions. And this has been, these efficient sampling techniques have been built upon like a huge line of literature spanning many decades. And so we're in luck. When this utility function is piecewise concave, this exponent of that utility function is piecewise log concave. So it's log concave on each piece. So we're kind of in luck. We can rely on these techniques for sampling, for efficient sampling. And just to say, these, I'm not going to talk about these techniques too much. We use them as a black box, but they rely on like random walks. And this is a random walk, just so everyone knows. Okay, so I'm going to tell you our theorem, and then I'm going to tell you exactly how we rely on those efficient sampling techniques. So, theorem. Suppose that our utility function is piecewise L-Lipschitz and concave over convex regions in some parameter space Rd. There is an epsilon delta differential privacy algorithm that approximately maximizes U sub s of rho, this utility function. And its running time is polynomial in the dimension, the Lipschitz factor, epsilon and delta are privacy parameters, and the size of our sample. Okay, and I'm going to tell you more now. Yeah?
Do you mean, when you say L-Lipschitz and concaves over convex regions, do you mean like each piece is a convex set?
Yeah, the piece.
So like the different pieces all form convex sets? Okay.
Yeah. Oh, and it's also, I'm sorry, I forgot this factor. It's also polynomial in the number of convex sets that we need to optimize over. So I'm going to tell you what the algorithm looks like. So step one, remember, okay, we want to run the exponential mechanism, but that's hard. So we want to approximate the exponential mechanism. So the first thing we do is we estimate that the probability mass the exponential mechanism places on each piecewise portion of the domain. Okay, so like we've got all of these piecewise portions, we just estimate the probability mass that the exponential mechanism puts on each of them, and this requires an integral estimation algorithm, which is by Lobush and Bancala. And then we sample a portion of the domain according to those probability mass estimations. So like I've sampled this red piece, maybe. Okay, and now I've got this red piece, and then I just sample a point in that portion of the domain with probability that's approximately that which the exponential mechanism gives. And this requires approximate sampling, and we use this technique by Vasily et al. From 2014. So it's pretty simple, and that's the algorithm. And so all we have to do is show that the output distribution is approximately the same as that of the exponential mechanism. And differential privacy just has all of these really useful composition theorems and just theorems that you can use when proving that an algorithm is differentially private. So like we can use the fact that if an algorithm A's output distribution is epsilon tilde close to that of an epsilon differential private algorithm, like the exponential mechanism, for every input data set S, then that algorithm, which approximates the exponential mechanism, is 2 epsilon tilde plus epsilon differentially private. So just by showing that these two distributions are close, like our algorithm is differentially private as well. Like it's big O of epsilon 0 differentially private. And I'm kind of lying, it's actually epsilon, big O of epsilon and delta differentially private, but that's like kind of a technicality. Our approximate sampling techniques fail with some delta probability, and so when your algorithm is only epsilon differentially private with probability 1 minus delta, it's actually epsilon delta differentially private. So it's just kind of a technicality there. Yeah, so those are our privacy areas. Colin?
Does the epsilon tilde close, does that mean that on every input the distributions are close?
Yeah.
Or does it mean like most inputs?
So I should have said it's close under this metric, this what they call a relative metric, which is like you take the sup, so say you have two distributions mu f and mu g, and they have some density functions f and g. It's the sup of the log of f of x over g of x. So that's what I mean by close. Yeah. Any other questions? Okay. Cool. So great. So now I gave you my epsilon delta. I told you our algorithm is epsilon delta differentially private. I gave you a really quick proof sketch. But now, I could give you a really simple differentially private mechanism. Like I can output 0 no matter what sample you give me. Right? That's differentially private. It reveals nothing about the sample. But it's going to give really bad utility guarantees. So I also need to show that our algorithm is good in terms of utility. It approximately maximizes the utility function. So that's what I'm going to do next, utility guarantees. Okay, and so I'm going to tell you what our utility guarantees are, and it contains a term that I'm going to define next. But I want to motivate the definition of this term. So suppose that our utility function is WK dispersed, like whatever that means. And it's piecewise L-Lipschitz. The parameter space is contained in a ball of radius r. Let p hat be the parameter vector that our differentially private algorithm outputs. We prove that with probability of at least 1 minus gamma, the utility of this p hat is at least the maximum utility possible minus this term, which depends on h, the range of our utility function, the size of the sample, epsilon, which is one of our privacy parameters, d, the dimension of the space, r, the radius of the ball containing our points, and w and k, which are like our dispersion parameters, which I'm going to define next. And the important thing about this bound is that as you grow the number of samples, this utility loss goes to 0. Modulo the Lipschitz term, which I'll describe next. We can normally set w so that it also goes to 0 as s goes to infinity. So now I'm going to tell you what WK dispersion is. So roughly speaking, every private algorithm needs to add some noise to its output. Right? I told you it has to be randomized. It needs to add some noise to its output. So that means we kind of have to ensure that nearby parameters are similar. They have similar utilities. And we often guarantee that nearby parameters have similar utilities by assuming the utility function is somehow nice. Like it's convex, it's Lipschitz, it's somehow nice. But what about when our function is piecewise? I showed you like that average revenue curve. It was piecewise. Our function is almost always piecewise in these algorithm configuration problems and these auction design problems. So what does it mean for a piecewise function to be nice? Well, what we define a nice piecewise function as is that like the boundaries between the piecewise portions are somehow like nicely dispersed. That's what we need. That's what we define nice to be. So if you imagine if they're all bunched together, then if we move just a little bit on the x-axis, our y could change a lot. But if our boundaries are kind of spread out, well, unless you're like really close to a boundary, then when you change your x-axis a little bit, then your y-axis is probably going to stay about the same. So that's kind of the idea of WK dispersion. Formally, let P, which is P1, P2 up through PT, be a partition of the parameter space, such that the utility function is piecewise L-Lipschitz within each partition Pi. And I'll draw this next. But we say that U, this utility function, is WK dispersed if for every ball of radius W, the number of sets in P that intersect that ball is at most K.
Can you remind me, so in the coffee example, if it's dispersed, this means that everybody has wildly different views about the value of the coffee, or how?
Not wildly, just like they don't have wildly similar.
Not wildly similar.
Yeah. So I'm just going to give a picture of this partition. So like these are all the partitions of the x-axis such that the function is Lipschitz on one piece. And so a ball in the x-axis is just going to be an interval, and let's say this is a ball of radius 1. So as you can kind of see from this picture, even if I ranged this ball over the x-axis, like it could only ever intersect 3 parts. 3 parts of this partition, right? So we say it's 1, 3 dispersed. 1 is the radius of the ball, 3 is the number of partitions it intersects. Okay, so now I'm going to return to my theorem that I mentioned before. Suppose the utility function is wk dispersed, then we get this utility guarantee. And you can see there's a trade-off between w and k. So it's not exactly clear, like, what do I want w and k to be? And I just want to mention, a single utility function can be wk dispersed for many different values of w and k. Like here it's 1, 3 dispersed, but what if I choose a ball of radius 2? Then you can see as you range this ball over the x-axis, it's only ever going to intersect like 4 parts of the partition. So it's also 2, 4 dispersed. And the kind of important part is that our utility function holds for the best value of wk, like the value of wk that minimizes this loss. So you don't even need to know w and k a priori. We just guarantee that for the best w and k that minimize our loss, that's the maximum loss you're going to get using our algorithm with probability at least 1 minus delta. And so now I just want to go through an example of what this wk dispersion might look like in a pricing problem, a multi-item pricing problem. So in this multi-item pricing problem, there are 2 goods for sale, for example, a coffee and a muffin. Again, we have a distribution over buyers. Buyers' values are denoted as before. I'm assuming they're additive, just for simplicity. So the amount of revenue I can extract from this orange person, given prices P1 for the coffee, P2 for the muffin, just the price I can extract for selling the coffee at price P1, plus the price I can extract for selling the muffin at P2. So it's exactly the same as before. Again, our pricing algorithm, our learning-based pricing algorithm, gets a sample of individuals from this distribution over buyers. And again, it wants to maximize average revenue over the sample because learning theory tells us that this will maximize expected revenue over the distribution. Okay, so what I'm going to tell you, and I'm going to ask you to believe me, is that the average revenue in this multi-item pricing problem, the average revenue over a sample of a pricing mechanism is piecewise linear, and it's 1 Lipschitz. So I'm not going to explain that, but it's really actually easy to show. So if I've got like the price of the coffee on the x-axis and the price of the muffin on the x-axis, price of the coffee on the y-axis, then I haven't shown the average revenue function, it's on the z-axis, but I've drawn like partitions of the parameter space, and I'm telling you like on these partitions, the average revenue is piecewise linear in Lipschitz. And so I want to know like how dispersed is this average revenue function. Remember, so that means I want to figure out if I have a ball of radius w, how many partitions will intersect this ball, any ball. So how dispersed is this utility function? Well, it depends on this distribution over buyers, as you can imagine. So so suppose that I'm just going to define this function, f sub I of v, to be the density of the distribution over the typical buyer's value for item I. So like I've got this distribution over individuals, and that defines a distribution over their values for each of the goods. Item I is like, so this is maybe their the distribution over their value for the coffee. Suppose there are at most m items, and suppose that if I look at the maximum over all items I and over all values v, the density of f sub I of v is at most kappa. So that's an assumption. Suppose that this is true. So this kind of means that, like I was saying, like their buyer's values for a good are not like wildly compact. Like there's some kind of nice smooth and not like there's no point mass in this density function. Then we show that with probability at least 1 minus gamma, this utility function, average revenue, is wk dispersed with W being gamma over S, which is the size of the sample, kappa, which is the bound on the density, and the square root of M, which is, M is the number of items, and K is M. So now I'm going to remind you of what our utility guarantee was and how this W and this K factors into our utility loss. So let rho hat be the price vector output by our differentially private algorithm. We show that with probability at least 1 minus gamma, the average revenue over the sample of rho hat is at least the maximum revenue possible minus a term which is, it's just like we plugged W and K from the previous slide into our utility loss. And you can see, indeed, this utility loss goes to 0 as the number of samples grows. And I also want to mention that we show, I've given you some really simple examples of pricing problems where our differentially private algorithm applies, but we also show that our differentially private algorithm has strong utility guarantees in many other settings, such as when there are multiple bidders. I've only shown you single bidder settings. When the buyers have unit demand valuations, I showed you additive valuations. Unit demand is just another type of valuation. General valuations, and also other types of auctions like second price auctions with reserve prices. And so now I'm just going to summarize the talk. I showed you a private algorithm for maximizing a piecewise Lipschitz function, and I showed you it has applications in algorithm configuration and auction design and pricing design. And I'm just going to summarize here. So when the utility function is piecewise concave and Lipschitz, and the parameter space is multiple dimensional, then we get an epsilon delta privacy guarantee, and it's efficient because we rely on these efficient sampling techniques. When the utility function is piecewise Lipschitz, and the parameter space is single dimensional, we can do even better in terms of privacy. We get epsilon 0 differential privacy, and it's efficient as well. And what I didn't talk about at all is another algorithm we have. It's very general. It holds for piecewise Lipschitz functions. It holds for multiple dimensional parameter spaces. It has really good privacy guarantees, epsilon 0 privacy, but it's not efficient. It relies on kind of a discrete exponential mechanism. So this discretization of the parameter space grows exponentially with the parameters, the dimension of the space. Okay, so I'll take any questions now. Yeah.
So I guess the hard case is when the valuations are very similar between people, right?
Yeah.
But it's sort of, if you back away from the proof and just think about that by itself, it's kind of counterintuitive. It seems like when everybody is very similar, it should somehow be easier to maintain differential privacy, right? Because changing people shouldn't matter that much. So do you feel like it's just an artifact of the proof, or can you give some intuition as to why it makes it harder to?
Yeah, so I think, so differentially privacy is like a worst case guarantee, so it should hold even for worst case neighboring databases. So maybe for the vast majority of my distribution over buyers, they all have very similar guarantees. So if I change, most of the time when I change to a neighboring database, the function change stays almost the same. But maybe for 1%, a tiny percent, some guy has a very high value for a coffee, then when I change, in the worst case sense, when I change to a neighboring database, the function could change a lot.
All right. If there are no other questions, let's thank your speaker one more time.